Yeah. Am I audible?
Sir.
Yeah, so I got disconnected. So yeah,
Okay.
I'm sharing my screen again. Mm, yeah, is my screen visible?
Yes, sir.
Okay, just a sec. So yeah. Yeah, so we're discussing about these expressions. So now if we consider small signal analysis, so small signal is basically perturbation about the operating point or the steady state values. So if I consider ILTS to be one state, so this is its steady state value is capital IL plus where there is some perturbation IL tilde. Similarly we will have V naught TS will be equal to some V naught plus there will be some V naught tilde where IL tilde is much less than IL and V naught tilde is much less than V naught. This can be said. So considering this, what we can say is L d IL tilde by dt equals to Vg tilde minus capital D dash V naught tilde minus no plus D tilde capital V naught. Agreed? Yeah.
Sir, D dash tilde and
Yeah. So
D,
D dash
D
is what?
delta.
1 minus D, right? So
Yes.
consider this to be 1 minus D V naught. Now if I expand it, so minus 1 minus capital D minus D tilde
Okay.
into
Okay.
capital V naught plus V naught tilde. Now
Okay.
V naught tilde and D tilde won't both are small quantities, so it will be zero neglected actually. So what we have essentially is minus 1 minus capital D into V naught tilde minus this minus and outer minus becomes plus D tilde capital V naught, and there is another term capital V naught into 1 minus D. This is the steady state part, and this will be equals to 0, and the other term that is V naught tilde and D tilde that we are neglecting, so hence we get this. So from here only I have written this. Similarly we can write for the KCL, which is C V naught tilde by dt is equals to uh, again D dash IL tilde minus D tilde capital IL minus, and here comes the part. So if it, since it's a constant power load, so P remains constant, right? So it becomes plus P by V naught square V naught tilde, right? Any
I'm not getting, sir, but only the calculations, I think.
this part, so P is constant,
That.
right? So 1 by
Yes.
V naught. So if you consider, just a second, yeah, so If you consider this portion, so P is constant, right? So minus P by V naught. Now P will be P is constant, so under any perturbation there won't be any perturbation in the power, right? So
Okay.
what we essentially have is capital V naught plus V naught tilde.
Okay.
This can be written.
Yes, sir.
Okay, so now this is equals to minus P by now this you can take the capital V naught out. This can be written as 1 plus V naught tilde by V naught, capital V naught.
Okay.
Now this is a standard binomial expansion. So
Okay.
sorry. Um, hmm. So if we keep this V naught, this portion 1 plus a V naught tilde is much less than V out. So this expression is way less than 1. So we can write this as 1 minus V naught tilde by V naught plus V naught tilde by V naught whole square. This binomial expansion goes on. So we truncate the higher terms since they are very small. So we approximate it to this part. So this can be then written as, so this is the constant part, P minus of P by V naught. So this is the steady state part, and it becomes it cuts to 0. So this part at under steady state is 0. So 1 minus d capital IL minus P V naught equals to 0. So this part becomes a steady state part, and the non-steady state part becomes plus P by V naught square V naught tilde.
Okay, sir.
Clear? So
Great.
once so this can be written now to express this in terms of state space expressions. We can write them as dIL tilde by dt dV naught tilde by dt equals to so our first state variable is IL. So IL, so here we don't have any terms of IL, so it's 0. V naught tilde term we have 1 minus d dash by minus of d dash by L. Okay, and here we have IL tilde term which is d dash by C, and we also have V naught tilde term which is P by V naught square C time this into IL V naught tilde so remaining part will be the input matrix.
Input.
Yeah, so input matrix what we have in the second case we have IL by C minus of IL by C, and in the first case we had V naught by L, V naught by L, this times D tilde plus we have 1 by L and 0 times Vg tilde. Now what is more important is we have to analyze the state matrix. So this will give us the idea of stability. So how do we know about the stability? The eigenvalues of
Eigenvalue.
this state matrix will always be what? Negative or positive?
Negative.
Why?
Si minus a mod will be a 0. In that the Sir, repeat the question once again.
No, I am asking that why are you considering that it will be negative?
In the expression, we need to find out the roots of that one. The value should be in the S, right of left side
Yeah,
of
yeah. On in the
S plane.
left hand side of the S plane,
S plane.
the poles should be. The poles are equal to the eigen values of the state matrix,
Yes, sir.
right?
Yes, sir.
Okay. So let's derive the eigenvalues. Or we can do another thing. We can go for the characteristic expression. So how to find out the characteristic expression? You just said
Si
Si
minus A
minus A equals to.
mod 0.
So this is the expression for characteristic equation, right? So okay, let's do this. So we have a 2 cross 2 matrix. So S0 0 S minus, we have this 0 minus d dash by L, d dash by C, and P by V naught square C mod equals 0. This implies mod of S d dash by L minus d dash by C S minus P by V naught square C. So its determinant needs to be found out, which is equals to S into S minus P by V naught square C plus d dash square by LC. This is equals to 0, or S square minus P by V naught square C S plus d dash square by LC equals to 0. So now can you identify that why this operation is unstable?
The roots are positive.
Roots are positive always. So P is, you cannot provide negative power, so P is always positive. V naught square is positive. C is, being a parameter value, positive. L, C both are positive. D is by definition lies between 0 to
That
1,
will be positive.
and this will also be positive. Hence this
La-
operation is not possible, and hence I am coming back to your first question, that why is there a resistance. We place a resistance in parallel with this. So when we add a resistance, so what does we have here? We will have here we will have minus P by V naught minus V naught by R
Okay.
addition. So I am writing it with a different ink. So these are the changed. So this will be minus V naught by R. Yeah.
Yes,
Here
sir.
also. Correct. Hello.
Yes, sir.
Correct, right? So here will be its V naught by R. Now here we will have a minus V naught tilde by R. Then how does the characteristic how does the state matrix change? So only the state matrix will change, and it will have a quantity here as minus 1
1
by
by
RC.
yes.
Now here we will have a minus 1 by RC, and here we will have a plus 1 by RC. So a plus 1 by RC, which results in a plus 1 by RC times S. So we will have S square plus S into 1 by RC minus P by V naught square C plus D dash square by LC. This equals to 0. Now we can stabilize the system. How? Considering this constraint, 1 by RC will be greater than P naught by V naught square C, which implies that R will be less than V naught square by P naught.
Okay.
So this is a stable. Yeah. So this is. This is the stability criterion for constant power loads. So we require an additional resistance in the load, which is a constant resistance, and its value should be less than V naught square by P naught, which is the steady state resistance as observed by the from the converter of the constant power load. So R should be less than this resistance.
But V naught will be the variable, right, sir?
V naught, yeah, it's variable, but you will operate it at a operating point, right? So at that operating point, V naught square by P naught is the tangent of at that point. So
Okay.
that magnitude, this magnitude of this resistance should be less than the magnitude of that resistance.
Okay, sir. But in the lectures, the expression was given as in different way, right?
Let's see. No, this is only
This
given.
one is okay.
This is only it. See,
Uh,
P CPL is less than V naught square. This is UC square, whatever you say, UC square by R. So just put P naught here, put the R here. So P naught will be less than V naught square by R.
okay, okay.
Same criterion. So that criterion is only provided here. Okay. So the power, so here the stability criterion is given with respect to power. What I have said is with respect to the resistance observed. So you can also say the criterion in terms of power. So power of the constant power load in the stable system must be less than that of the resistive load. So how much power the resistive load is consuming, the power consumed by the constant power load must be less.
Okay.
So that should be satisfied for stability, uh, to obtain stability. Now what we have is, yeah, yeah. So I think that's what was about in this lecture. So let's go to the next one. So in this one, first of all, do you have any doubt regarding the
Sir,
stability of? Yeah, go ahead.
regarding the CPLD loads only, how it is, what are the CPLD loads, sir?
Oh,
Constant.
what are CPL loads?
Hmm.
Like mm, uh, electric furnace is a CPL load. So
No, no, sir. In this, in the lectures itself, there it is given that around 80% are the in 35th lecture, I think.
35. Okay.
In this one only. Just move upward.
Yeah.
Yes,
Typically,
80. are constant power loads, and 15% are the resistive load.
Hmm. Constant
It is
power
given.
loads. Okay. This I don't know about this numbers, but if you want examples of constant power load, it's basically the furnace, electric furnace application is an example of constant power load.
But in the lectures, sir has constantly telling that power electronic converters loads are the constant power loads. He is saying converter loads means whichever the converter, inverter, and the DC to DC converters which are used for the any application that comes under as a constant power load.
Please come again. I couldn't hear you properly.
Sir has constantly telling that eh, all the power electronic converters are the constant power loads, CPLDs.
Mm, Power electric converters can be operated as a constant power applications, but not all of them. They can be controlled in such a way that they will operate as constant power load. That's true, but will they be?
He said in the I have remembered that 80 to 85% means all the SMPS are the constant power loads. He said all the laptop chargers, all the desktop, all the have the constant power loads. He said why he told like that. I am not able to understand that one. Uh,
Laptop chargers. Uh, See, all battery related applications. What happens in battery charging is firstly there is a constant current zone where the battery is charged under constant current, and then it is operating constant voltage. So how come it can? I don't know. I have no idea about that, but
okay, sir.
constant
Okay.
power load as such is uh, furnace application, and there are some converters whose uh, characteristics is like a constant power load. Means it can be operated as a constant power load if it's controlled in such a way that the power input will always be constant. So it can be controlled in such a way, it can be
Okay.
characterized in such a way, but its application I have no idea.
Sir, just move upward, sir. In the downside,
This
in 35th only, in the
30
last, in the 35th lecture only, the V square all the time.
30 at bottom
Bottom one. These two conditions are given, right?
here.
They mean this one and in the downward only.
Hmm. Okay, acha, here is more things are given. Just let me check what it is. Uh, here, this is the part. Okay. Even at operating point. Hmm. Acha, now it is considered as with an electrical system. Last time, the last example that we took is with a boost converter, right? So
Okay.
here it's just showing an electrical system. So this is a voltage, and you will have a you will obviously have a RLC network in between. So this R and L will determine the resistance and inductance of the cable that is there, and then you have a capacitance to hold the voltage at the output. So this is a
And why it is given as 2P by V?
2p by v.
V not.
Okay, just let me check once. Okay, the RCPL, the resistance that I told, no, the tangent is the resistance, so it's like an hyperbola. So the tangent, so the expression of tangent can be written in the form as 2 I naught minus 1 by RCPL, and which can be written equals to 2 times P by V naught minus P by V naught square into V.
The representing of the curve one.
So this I think this will be the current ICPL. This is not R. Okay, let's derive it. Just so the thing that is provided is plus minus E. This is the resistance and inductance and the capacitor, and there we have the constant power P. Okay, so now so this is V out, this is I out. So D, so what we have is V out into I out equals to P, so it's constant. So what I can write is I naught equals to P by V naught. So d I naught by dv naught equals to minus P by V naught square V naught. Okay. So yeah, minus P by V naught square. Oh sorry, we do not need this V naught. It's because we have already put it d I naught by dv naught. So it's minus P by V naught square. Yeah, correct. So this is the expression. Okay. Now, as can be observed from equation 4, that RCPL. Now, what is RCPL? RCPL is given equals to minus P by RCPL. This will be actually equals to 1 by RCPL.
Yes, sir.
Right?
Yes, sir.
Now, so this should not be P. This will be 1.
1 that is 1.
So yeah, so okay, so 1 by RCPL equals to P by V naught square, minus in the sense because RCPL is considered to be positive, so hence the minus is kept, and 1 by RCPL. Okay, as can be observed from equation 4, the RCPL is dependent on the actual voltage and current because it's dependent on P and V naught square. Okay, so the curve represents the current versus voltage for RCPL can be approximated as straight line. Okay, it can be approximated as straight line. So the straight line expression will be like this. So it will be, let's say I have I naught equals to so let's find out the expression, so that will be much better. So this is V I, so let's consider this. So now we have two expressions. So this is so this is I and this is I1 and this is I2. So V1 V2, so I1 minus I2 by v1 minus v2 equals to minus p by v naught square. So this is equal to so how to find out the expression. So this is the straight line, this will be the straight this straight line. This is the straight line. Now what I need to find out are these asymptotes. So so I will write this to be, so we will how to find this out. Now the slope is known now, but how to find out the intercepts made by the straight line?
Sir, just show the slides. Just move upwards. That 2I naught is being from the not this one, this curve, just circuit one.
Circuit, this one.
Here, V.
Just this will be done actually. Well, like if you can find out the intercepts for the straight line, we can so this will be how to find out this.
The expression is wrong, sir. I think I1 minus I2, what you have written is
Here.
Tan.
So I1
That is
minus
what you
I2.
have written for the straight line, or for the tan, for
The
okay,
tangent.
okay, okay. The expression is wrong.
The
Okay,
expression of tangent will
fine.
give you the straight line. Now this is okay, but what I need to find out is what will be the oh, I have it. Ade. So one point I have is I naught and V naught, right? I naught comma V naught.
Yes,
This is a point on the straight line. So what I have essentially is, so y equals to mx plus c is my straight line. I have the slope y equals to, I have the slope which is minus p by v naught square, minus p by v naught square. This is the slope x plus c, and to find out c, place I naught and v naught. So y will be capital I naught equals to minus p by v naught plus c. So c is equals to I naught plus P by V naught. Hence the expression will be I naught, with I don't know what I naught is, but the tangent expression is I naught equals to capital I naught plus P by V naught minus P by V naught square V naught. Now let's see the expression. So I naught is what? I again V naught into I naught equals to P naught. Hence this can be written as equals to twice P by V naught minus P by V naught square small V naught. So it's
Okay.
yeah. So
Yes.
that's how the expression is coming of I naught equals to 2P by V naught minus P by V naught square small V naught. Just one correction should be done, that is this P will be equals to 1. Okay.
Okay.
And now having this, we can express the constant power load as this expression, right?
Okay.
So we have 2P by V naught, so there is 2P by V naught current sink and minus P by V naught squared, so this gives us the RCPL. So from there if we go, we have this characteristic expression. Now neither this coefficient nor this coefficient can be negative, which gives us these two conditions.
Okay.
So from these conditions we get the stability criterion under this scenario. So the first one was with respect to a boost converter. Here we are just connecting with a normal source through a we are connecting it to a normal
NC
source
filter.
which has a system resistance inductance and a capacitance RLC. So then we are observing how it, what will be its characteristic, what will be its stability criterion.
And this one P is less than minimum of.
Okay, so this has come out. Now let's see, replacing RCPL by this inequality, the relation 11 is obtained. Okay, so oh, so RCPL will be less than minus R from here, and RCPL will be less than minus L by RC from this expression. So we can write, so what are our criteria? RCPL will be less than minus R and RCPL will be less than minus L by RC, right? So hence together we can write RCPL will be less than minimum of minus R comma minus L by RC.
Okay.
Now
From that R is replaced by.
yeah, now the R can be replaced, no, you know, not R is replaced, so RCPL is this, now RCPL can be replaced by P, no, yeah, so this can be replaced by V naught square by P
P.
will be less than minimum of minus R comma minus L by RC. Now divide both side by V naught square and take this side and this one and this side, so P will be greater than minimum of minus V naught square by R, or not minimum, it will be maximum I guess, no minimum only. So it's V naught square by R comma minus V naught square RC by L, V naught square RC by L comma V naught square by R. From here the criterion comes, just converting the inequality expression from resistance to that of power. Okay.
Okay. Okay.
Okay. So next what we have is the continuation of this, and yeah, any question here in this one?
Here, this one I am not able to understand, sir. The Z input one and Z source
Z.
impedance match mismatch. Impedance mismatch concept, sir has discussed, but I am not able to get that one.
Okay. Okay.
Uh,
Which part? Still
this the diagram has given, right?
this one.
This one. Uh,
Okay. So this is basically, this portion involves designing of the input filter design, this lecture. So in this lecture what
okay.
is done is we need to design, we are given this, the converter. Now we have to design an input filter in such a way that no what should I say, no ripple in voltage or current should be reflected on the input side. So that's why we need an input filter. So what it
Okay.
does is it flattens the curve drawn from the supply side, and it attenuates the high frequency component at the input terminal. So that is the main idea. So this portion is not related with the stability.
Okay.
This portion is related with the input filter design, so that there is no ripple or harmonics present in the input current. So the harmonics in the input current are flattened or attenuated. So to design this input filter, what we need is so to design this input filter, we need to, so this is the plus minus VD, see, and here we will have some VS. So considering the small signal variables of both sides, what is ensured precisely is V so this is the supply VS, and this is the input filter. So here we have the plus minus VDC. Now what you need to ensure is this. So this is the current IS tilde, and this is IDC tilde. VDC tilde by no, not VDC tilde, VS tilde by is tilde, this should be infinite. So any disturbance on the input side will not affect the this side. This should be very high, not infinite. This is ideally infinite. This impedance must be very high. Alright, so once that is ensured, the input filter will behave properly. Now the exact way of designing the input filter, you can go through this chapter in this book, Robert Erickson, Input Filter Design.
Okay.
So that contains all the necessary procedure needed in designing the input filter. The main focus is that any harmonics in the input side must be attenuated. That can be only ensured by making the impedance for the harmonics to be much higher on the input side. So that's the main idea. Now the procedure you can find in the book. So that's what this portion is all about. Okay.
Okay.
And so this is again, there is a discussion on the constant power load. So now here it is shown there is a R in series with the capacitor. So this becomes a damping circuit, and it behaves as a passive damping for the constant power load. So again, this can be shown. So this kind of expression comes up. So again it can be shown that there will be a criterion of this R for which the whole system stabilizes. In the same way we can analyze it. So we need to find out the characteristic expression, and once we obtain, so this bottom portion is the characteristic expression. So once we can obtain this, we can also obtain the criterion for stability using passive damping. So same kind of analysis. So any question here you want me to address, or do you want me to show this?
No, sir, no, sir. Because I have not gone through these lectures. These
No, this
Hello.
is exactly the same way, just the earlier one that I did, this one.
Okay, sir.
It's
Okay,
the
okay.
same way you
Because
need to derive the characteristic expression. You will get the coefficients. Now to make the system stabilized, all the eigenvalues must be all the all the eigenvalues must be negative, and hence you will get some criterion. So hence the coefficients of the characteristic expression will always positive. So now to make them positive, what are the criterion? So you have this is the characteristic expression. So you can see this expression can go negative, this expression can go negative. So from these two,
without Harvard's
it's a cube term. So you have to go for
RH criteria.
Raut-Hurwitz criterion. So you know, right, Raut-Hurwitz?
Yes, yes.
So you through Raut-Hurwitz criterion you can find out these expressions. It's the same way. So that was second order, so we could do it directly. In the third order system you need to go through Raut-Hurwitz criterion, and you can find the expressions. That's it. Nothing else is there. Same analysis. This again, this circuit only, same analysis. Okay.
Okay.
Okay. So now let's go to the next one. Yeah, next one we have something very interesting. We have the criterion, some special criterion method to analyze the stability criterion. So the first method that we are going to discuss is the Middlebrook criterion. So what does Middlebrook criterion state? Middlebrook criterion states that a system will be stable provided that the Nyquist contour of ZS-YL remains within the unit circle. Now what is ZS? ZS is the source impedance of the converter and YL is the load admittance of the load connected. So ZS is the source impedance and this is the load admittance. So how the proof comes? Let's see. So firstly, let's take a system. Vs, this will be ZL, Zs. So we are considering the Thevenin equivalent of both source and load. Clear? So whatever it can be, but we can represent it with a voltage source in series with a load impedance. So with an impedance, right? Yeah.
Yes, sir.
Similarly, we can do it for the load portion. ZL, some plus minus VL, right? Now let's analyze this. So the so here also it has been shown Vs, both side two impedances and a VL. Now what are we interested in is this voltage plus minus V. So first we need to find out the current I. I equals to Vs minus VL by Zs plus ZL. Now V will be equals to Vs plus minus I Zs, which is equals to Vs minus Zs Vs by Zs plus ZL plus VL Zs by Zs plus ZL, which can be written as ZL Vs by Zs plus ZL plus VL Zs by Zs plus ZL. So this is the expression that has been obtained. Now Zs will be written in terms of Ns by ds and ZL will be written in terms of NL by DL. It can be easily written. So V equals to, so ZL will be written in terms of NL by DL. Zs will be written in terms of Ns by ds. So this one can be written as NL by dl vs divided by ns by ds plus nl by dl plus vl ns by ds whole by ns by ds plus n l by dl. Now what we are going to do is this equals okay. Now we will simplify this. Then we return equals to so we will multiply up and down with ds into dl. So we will obtain nl dsvs plus vl ns dl divided by, we have nsds, so it will be nsdl plus dsnl. Now we are going for the consideration. So what we will consider, so we have some considerations in this. Considerations. The first one is the load is doesn't have right half zero.
The screen is not visible.
Yeah,
Screen.
screen is not visible.
Yes, sir.
No, it's showing visible on this side. Visible?
For
it's now?
me,
Yeah.
no, sir.
Just a minute.
Just now it has gone out.
Okay, just now is it visible?
No, sir.
Okay. Now it's
Now it's visible.
Now it's visible, right?
Yes, sir.
Okay, so load doesn't have a right half pole. This is the first criterion. When supplied by an ideal source. The second criterion consideration that we will make is that the source the source is a stable source, meaning there will be no right half poles in ZS. Now taking these considerations, that we have this source is a stable source and the load doesn't have a right half zero. So when does load have a right half zero?
Sir?
When does loads have a right half zero?
Right half 0.
Yeah.
Don't know, sir.
So right half zero only occurs when there is a switching when there is a power electronic converter or when there is a switching circuit in between two energy elements, then only we observe a right half zero. So if you go through the small signal expressions for buck boost and buck boost, buck doesn't have a switching network in between the L and C. The L and C is on one side of the switching network, and hence
Okay,
it doesn't.
in the boost one.
In the boost, it is the inductor is on one side, the capacitor is on the other side. Same goes for buck boost. So hence there is a right half zero.
Okay.
So
So these considerations for we need to take or
no, these are the considerations that are taken to to provide the criterion which is known as Middlebrook criterion.
okay.
These are not made, like, this is done by the one who has made the criterion. Professor Middlebrook
Okay.
has made this criterion. So from there, so once we know that the load doesn't have a right half zero, which means that NL has no right half zeros. And when source, I'm saying source is a stable source, we don't have a right half pole in ZS, which means that DS is again there is no right half element. So what we can write is NLDS VS plus VLNS DL divided by, we can take this DS into NL outside. What we are left with is 1 plus NS by DS. NS by DS is your ZS, and DL by NL, which is your YL. So since there is no right half element in this side, the right half elements can only be in 1 plus ZS plus YL. So if we consider the Nyquist contour, for ZS YL equals -1, we can determine the stability of the system in terms of Middlebrook's criterion. So in case of Nyquist criterion, what we had is GH equals to -1, right? So around -1, how many times it's taking rotations? How many rotations are it making? That gives us the Nyquist criterion. In
Yes,
same
sir.
way, if we go for ZS into YL and we see how many times it is rotating around the -1, 0 point, we will get the stability criterion for this for any electrical system in terms of Middlebrook criterion.
Okay. After all the this we should be having this transfer function, which is to be -1 rotations.
Yeah, so
Uh,
no, not -1 rotations, around -1. So what is Nyquist criterion?
around -1.
Yeah,
Nyquist
so this is
criterion
the
should be
point
followed.
-1, 0. So how many
Hmm.
rotations are done around it? So there is no that expression, right, that P minus Z
Yes,
equals to
equal
number
to
of
number of
rotations
encirclements.
in counterclockwise CCW. So from there you can
Encirclements.
get the whether it's stable or not.
Ah, yes.
So that's it. That's only.
Total we need to check, or first we need to have the Nyquist criterion should be satisfied, and then NLD, the term 1 plus ZSYL should be removed, and the remaining part we need to check.
No, just ZS into YL you need to check. You need
Okay.
not go for the whole,
Okay.
because this is in the denominator, right? Whatever is in the denominator will determine
Yes, yes.
the
And
stability.
for remaining part of that one, DS into NL and
DS into NL is
the numerator.
already cleared out, because load doesn't have a right half 0, source is a stable source. So NL won't have any right half element, DS will also don't have any right half element. So we are
Okay.
not bothered about DS and NL. Right?
Yes, sir.
So that is what is Middlebrook criterion. But as you said that it is always not, in case of source you can say that yeah it will be a stable source. But in case of load you cannot say that it will always be such that there is a right half 0. There may be right half 0 in the load. As I said, in case of buck boost converter only, right half 0 crops up, right? So right half 0 may happen. So that's why there this criterion is not that much used. So yeah, so same thing has been told, since neither NL and DS have any zeros in the right half plane, it follows the interconnected system is stable provided 1 plus ZSYL does not have any zeros in the right half plane. So this again then comes with the Nyquist theory, and we have to check the closed loop system is equal to the number of clockwise encirclements of -1 made by the Nyquist contour of ZS into YL. So this is how you can observe the gain margin and phase margin accordingly from Nyquist criterion.
Okay.
So yeah, so that's it.
Sir,
And
why we need to do with the Middlebrook criterion then? Nyquist is there, Bode plot, all the things are there, right?
no. How can you apply the Nyquist criterion? Because Middlebrook has made this expression. So 1 plus ZS YL should be equals to 0, and now you are concentrating on ZS YL. This now is similar to the Nyquist criterion for stability.
Okay, I am asking that if we are if you are doing the converter, for the converter, we will do the average model for that one. Transfer function, we will find the transfer function, and we will do the Nyquist plot, or Nyquist criteria, or Bode plot for finding the stability and how relative stability.
Yeah, you can do, no issue.
The main advantage of
But
Middlebrook criterion is what?
the main advantage of Middlebrook criterion is that this is only, you are considering only for a single source and load. If there are multiple,
If multiple is given, then this criterion should not be used, right?
no, well, that's what I'm saying. If there are multiple loads and sources, you cannot go for Bode plot, right? How many Bode plots will
Yes,
you do?
yes.
So Bode plot is also an derived version of Nyquist criterion. It's more general, so you will get the whole picture using Nyquist criterion. That's
Mm.
it.
Okay, sir.
Okay.
Okay, sir.
Yeah. Any question?
No, 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 sir.
So yeah. So and then the last lecture actually comprises of non-linear techniques, sliding mode control and feedback linearization. So these are some control non-linear control techniques that are done. Honestly, I also don't know properly, so I
Okay.
can suggest you some book where you can go through these if you want to.
Oh,
So just
yes, sir.
let me write it down. The one is Khalid, nonlinear systems, and the second is Vidya Sagar, same by the same name, nonlinear systems.
These books are related to the power electronics or a
No, no, no.
general
This is
one?
control system in general.
Okay.
So there you will get chapters on sliding mode control and feedback linearization method. So,
Okay.
but
I also not gone through the lectures
yeah,
in
yeah,
this
but it is
last
not
week
that much
because
used. Yeah, yeah,
uh,
good.
because I have stuck in the 36th lecture, I think.
Okay, okay.
Not able to understand. I need to
Yeah, yeah.
go.
So this
I
is
will.
means in practical, if you ask, non-linear methods are not at all much used. The linearization technique is only used for controlling power electronics converters.
Okay, sir.
Non-linear techniques are very less used because since they are non-linear, you cannot get any idea or get any sense of how the stability, what are the stability margins, and how you will how the control algorithm is performing. You cannot get those ideas. So in 90% cases, the linearization technique is only used to control the power system, the power electronic converters. So, but if you're interested in nonlinear, you can go through the books.
Okay, sir. If sir, how we will know the trend of business in the power electronics?
Trend of business.
Business means where we are going in the renewable side. We are going means to find any good companies to do something,
Mm,
because you are doing the PhD in power electronics, right? Only, right?
yeah, yeah. But in renewable application, the works are being done in many places. Like in USA, also works are done. In India, also several things are done. But in renewable sector, I think personally is getting quite saturated. Uh,
In the renewable also.
yeah.
But yeah, I'm not seeing any application oriented. The microgrids are not coming properly.
There are several reasons
The
because
EV.
yeah,
We
see,
I have I know some reasons, but uh, commercially they are where we are going, like
oh, it's a
what to do.
commercially they are still not available because there are several problems associated with this which are yet to be
Mm,
addressed. But
okay.
as a topic, means whatever is there, everything is in explored. But now they have to be properly controlled. The control algorithms need to be properly made in order to make them commercialized. That's it.
Okay. Okay.
Like there are several problems. The whatever is being discussed in these lectures, these are all theoretically possible, but when you go for practical applications, there are several constraints associated with this.
Sir, can you tell me any power electronics based companies
I have no idea. In India,
in India,
no idea.
in US,
US,
or
there.
any some kind of to
No, I personally I have no idea.
okay. So what PhD people will do after their doctor? They will go for